In this video, we're going to talk about conditional random variables. Remember from the very first video that the definition of conditional probability is the probability of A given B, and that can be calculated as the probability of A and B divided by the probability of B. Now we're going to take that idea and apply it to random variables. So we define a conditional random variable, y given x equals x, is a variable where x is fixed and y is allowed to take on the values that it can possibly take in its conditional range. We can say that if y is a discrete random variable, then y given x equals x will also be discrete. And similarly, if y is continuous, y given x equals x will also be continuous. And this holds no matter what x is. So you could have a discrete random variable conditional on a continuous one, or vice versa. Or they could both be discrete or both continuous. Any mix is okay. We can also imagine that if y given x equals x is a random variable, it must have everything that a random variable has. So think about that. What do you know that a random variable might have that we could use? See if you can jot down. I can think of at least 7 things that every random variable has. Well, it's going to have a range, and in this case we call it a conditional range. It's going to have a probability function or probability density function. It'll have a CDF. It'll have a distribution, so binomial or Poisson. It'll have a conditional mean, a conditional variance, and even a conditional moment generating function. And there's other stuff it might have as well. So anything that a random variable has, x given y equals y will have. If we're thinking about the fully discrete case, where x and y are both discrete, we're going to define the conditional probability function of y given x equals x as follows. We call it p of y given x, and it's just the probability that y equals y given x equals x. Well, let's sub in the definition of conditional probability, and that's just equal to the joint probability function of x and y divided by the marginal probability function of x. We can also define the conditional mean, which is where we say the expected value of y given x equals x is the sum over all values of y in y's conditional range of y times this conditional probability function. Now notice, this entire expression is going to end up being some function of little x. It's not going to be a function of y because we're summing over all y. And that conditional range may or may not depend on x. If x and y happen to be independent, then this result will actually simplify. We can have the conditional probability function, and the top will factor into the marginal probability functions, and then p of x will cancel out. So the conditional probability function is just the regular probability function. And also, the conditional range will be the same as the regular range, since it can't depend on x. So that means that the expected value of y given x equals x, if they're independent, is just the expected value of y. And that should make sense because if x and y are independent, then knowing that x equals little x tells us absolutely nothing about y. It has the same average as it would have no matter what x was equal to. Let's look at an example. Imagine we have x and y being 2 Poisson random variables with parameters mu1 and mu2, and they're independent. And we'll let t equal the sum of them. We showed in a previous video that t is going to be Poisson with parameter mu1 plus mu2, but what can we say now about y given t equals little t? Take a second and think about that. Think about all of those 7 things we can say about random variables that we listed before. How many of them can you figure out for this particular random variable? Y given the total number of events in both x and y periods of time is equal to t. Well, we can start off with the conditional range. If we know that little t events occurred in total between x and y, then the number that occurred in y is just going to be between 0 and t. Y on its own unconditionally has no maximum, but if we know that t is equal to little t, then y's maximum is going to be little t. Next, we can look at the conditional probability function. Well, that's going to be p of y given t, and it's the probability that y is equal to y and t is equal to t divided by the probability that t is equal to t. Well, the top, we want to express that in terms of independent random variables because that makes it nice to work with. So if we want y to equal little y and t to equal little t, that's the same as saying y is equal to little y and x is equal to t minus y. Those will give us the same thing, but that's extra nice because x and y are independent. And so we can split up that probability into the product of those 2 probabilities on the top. And the denominator is just probability that t, the total, is equal to little t. Well, each of those 3 random variables, y, x, and t, are Poisson, so we can sub in the probability function for those random variables. We'll have e to the negative mu2 to the y over y factorial, for x is t minus y, and similarly for t is equal to little t. And some really nice canceling is going to happen. All of those e's will cancel out. We'll gather up all the factorials together, and then we'll have mu2 to the y and mu1 to the t minus y all over mu1 plus mu2 to the t. A little bit of simplification leads us to t choose y, mu2 over mu1 plus mu2 to the y, and then mu1 over mu1 plus mu2 to the t minus y. That should look familiar. So the next thing we can do is actually identify the distribution. The conditional distribution of y given t equals little t is binomial with parameters t and mu2 over mu1 plus mu2. And knowing that, that tells us instantly what the conditional mean and variance are. The mean of a binomial is just the product of the parameters, n times p normally, but in this case, t times mu2 over mu1 plus mu2. And similarly, the variance is n times p times 1 minus p, or in this case, t times mu2 over mu1 plus mu2 times mu1 over mu1 plus mu2. So that gives us all this information that we can find about the distribution of y given t equals t. Notice that these last two things here are functions of little t and not functions of y, as I said. All right, another example. This is related to what you just did in the tutorial. If we let x, y, and z be multinomial random variables, and suppose that we know one of them, that x is equal to little x, I want to find the conditional probability function of y given x is equal to little x. So that's the probability that all of those multinomial random variables take on those values, x, y, and n minus x minus y, divided by the marginal probability function of x. We can sub in those definitions, so we've got n factorial over x factorial, y factorial, n minus x minus y factorial, and then all of those p's. And on the bottom, we'll have n choose x, which we could write in terms of the factorials, p1 to the x, 1 minus p1 to the n minus x. Again, some nice canceling is going to happen, and we'll gather up all of those factorials. And then we have p2 to the y, p3, which we could write as 1 minus p1 minus p2 to the n minus x minus y, and then we could split up the denominator into two products. Simplifying, that's n minus x choose y, p2 over 1 minus p1 to the y, and then 1 minus that to the n minus x minus y. And the range is, again, from 0 to n minus x. So here we can notice that y given x equals x is another binomial random variable with parameters n minus x and p2 over 1 minus p1. See if you can think of a logical justification for that result. Why does it make sense that if we have a multinomial distribution and we know what the first one is, given that the second one is also a binomial random variable with these parameters? I want to see what happens now in the continuous case. Things are a little bit different here. So suppose x and y are continuous random variables, and they have some joint PDF, little f of xy, and marginal PDFs, little f sub x of x, and little y sub y of y. We can't use a probability function the way we did before, because if we wanted the conditional probability that x was equal to x given y was equal to y, that would give us 0 over 0 for two continuous random variables. Instead, we need to work with the conditional CDF and then take some derivatives. So for the conditional CDF, I'm going to define it to be big F of x given y, as the probability x is less than or equal to x given y is essentially near the value little y. We can use the definition of conditional probability, so that's the probability x is less than or equal to x and y is in that small range from y to y plus epsilon, divided by that probability. And on the top, we can write this by definition as the difference between the joint CDF evaluated at x and y plus epsilon minus the joint CDF evaluated at x and y. In the denominator, similarly, we have the probability that y is between y and y plus epsilon as the difference in the CDF of y at those two values. Then what we're going to do is divide on the top and the bottom by epsilon and let epsilon go to 0. And if you're looking at that and you remember your calculus, that's just the definition of a derivative with respect to the argument that has the epsilon attached to it. So on the top, that'll give us the derivative with respect to y of the joint CDF. And on the bottom, it'll give us the derivative with respect to y of the CDF, which is just the PDF of y. Okay, but what we really wanted was the PDF of x given little y. So that would be the derivative with respect to x of big F of x given y. And then subbing in what we got here, we'll have two partial derivatives, one with respect to x and one with respect to y, of our joint CDF, divided by the marginal PDF of y. And the top there is just the definition of the joint PDF. So we have the joint PDF divided by the marginal PDF to give us the conditional PDF of x given y equals little y. So notice it's the same idea as before. It's the joint divided by the marginal that gives us the conditional. Even though we got to it in a slightly roundabout way for the continuous case, it's basically the same final result as in the discrete case. It's a little bit harder to visualize though. It's hard to figure out what that really means to have conditioned on something that has a probability 0. So I want to illustrate that with a drawing here. Imagine we have the xy plane, and then on the z-axis here we have the joint probability density function. Let's say it looks like this weird kind of curvy surface here. And let's imagine we fix a value of y. So then we're going to sort of slice through this surface, and we'll end up with a cross section of this joint probability density function along the line y equals little y. And that slice there is basically the distribution of what x is going to look like if we know that y is equal to little y. So we need to sort of scale that up so that the area underneath that curve is equal to 1, and that gives us our conditional probability density function. So again, it's a little bit harder to visualize, but essentially we're taking a slice of the surface that represents our joint probability density function. And that's when we slice in terms of y equaling little y. If we were slicing in the other direction, perpendicular to what I have there, then that would be conditioning on x equals little x. So hopefully that makes a little bit of sense. We're sort of carving up the surface along one of the lines where y equals little y, or in the other direction where x equals little x, and getting a distribution of the resulting random variable. Let's look at an example of the continuous case. We'll use the same one that we used in the last couple of videos, our example where we had little f of xy equaling 3/4 x squared for 0 less than x less than y less than 2. And here we're going to look for the conditional PDF, the conditional range, and the conditional mean of both x given y equals little y and y given x equals little x. Previously, we had already found that the marginal probability density function for x was 3/4 times 2x squared minus x cubed, and for y was y cubed over 4. So we can just plug those in. The conditional probability density function of x given y is the joint over the marginal for y, which is 3x squared over y cubed. And now for the range, we need to think about what happens. The range of our joint random variables looked like this. It was that upper triangle. And so if we know the value of y, what does x go from and to? Well, it's going to go from 0 up to y. So for a fixed value of y, x goes between 0 and y. And similarly, if we want the conditional distribution of y given x, we'll take the joint divided by the marginal for x, and that gives us 1 over 2 minus x. For similarly, if we fix a value of x, y is going to go from x up to 2. And I want you to notice something for a second. The PDF that we got here for y given x equals little x is the PDF of a uniform random variable on y going from x up to 2. So that's kind of neat. That tells us that no matter what value of x we have, the distribution of y is uniform between that value and 2. Now that we have these, we can also find the conditional means. So the expected value of x given y equals little y, we'll take the integral over all x, which goes from 0 to y, of x times the conditional probability density function, dx. And you should try this, and you should be able to get 3/4 y. And second, we can take the expected value of y given x equals little x as the integral, which should give you x plus 2 over 2. Give it a try and see if you can either evaluate both of these integrals or find the result logically, especially for the second one. That makes it really nice because y given x equals x is uniform on x to 2, and you can just find the expected value of a uniform as the sum of the endpoints divided by 2. One last thing for this video, we can also remember from the first video the product rule. So the probability of the intersection of A and B can be written as either the probability of A times the probability of B given A, or the other way around, B first and then A given B. So we can also apply a similar result to random variables. If we know the conditional information about one random variable and the marginal information about one random variable, we can combine those together to get the joint information. And this can work both for probability functions or probability density functions. So we could get the joint probability density function as the product of the marginal PDF of x times the conditional PDF of y given x, or the marginal for y times the conditional of x given y. The same results exactly would hold if we had probability functions instead of probability density functions. So if you want, there's a couple of examples in the course notes illustrating this idea, but essentially we can use those rules and results from probability to do the same thing for random variables. And we can find either conditional probability functions or probability density functions, or joint ones, depending on the information that we have. All right, that is everything for this week. Next week's videos are going to talk a lot more about conditional random variables, conditional expectation, and conditional variance, and I will see you then.